In today's lecture, we want to talk about useful properties of the Z transform, and this is the first part of a series of 3 lectures. Actually, so there's a typo here. I'll fix it later in the slide. So this is part 1 of 3. So we're going to cover important properties of the Z transform, and in particular here, in this first part of the lecture, I want to talk about linearity, time shift, and scaling. So many of the properties that we'll talk about you've seen already with other transforms such as the Laplace transform. Maybe the main difference here is that you have to talk also about the region of convergence. So that's the main difference when it comes to the Z transform. The first property which you saw before, which is linearity, that says that the Z transform of a sum or a weighted sum is the weighted sum of the Z transform. The ROC here is the intersection because you want the both signals to converge, both signals that you're summing to converge. And this is why the ROC would be the intersection. Just to give you a quick example here. So let's suppose x of n is a left-sided signal, or let's suppose x of n is a, so this is the ROC of x of z. So let's suppose it's right-sided, so it's the outside of the circle, let's say. And let's suppose y of z is a left-sided signal. So this is the ROC of y of z, and it's left-sided, so it's the inside of the circle. And then, so for their sum, the ROC is gonna be the range, which is the area between these two circles, which is the intersection. So that's the important part. So you knew this before, but I just wanted to remind you of this property. So maybe linearity is one of the most important properties that we will use a lot in Z transform, but we kind of take it for granted actually because we use it without even thinking about it. And I would say maybe the second most important property that we're going to be using a lot is the time shift, which says the following. So if you shift the signal if you shift the signal towards plus infinity, so to the right by n0, this means the equivalent of this is multiplying by z to the power negative n0 x of z. So here's what I mean by a shift. So here you can see that the signal started at 0, 1, 2, and I shifted by 2 steps. So n0 is equal to 2 here. So what was 0 is 2 here. So here, let me write it down, that here n0 is equal to 2. Now, why does this make sense? So if you take, let's work with this example that we have here. So if this is, let's suppose this is, let's just take random numbers. So suppose this is 10, and this is 7, and this is 3, and also this is 10, and 7, and 3. Then you know that here, x of z is actually 10 plus 7z minus 1 plus 2z plus 3z minus 2, right? And this guy here, the shifted signal, is going to be equal to 10z minus 2 plus 7z minus 3 plus 3z minus 4. So you can see that the way you obtain, if you call this is the shifted signal, if we call it y of x, which is the shifted signal, so here y of z. And now this is y of z. And then you can see that y of z is actually equal to z minus 2 times x of z. So I hope so it follows immediately from the definition, but I hope you can see why this is true. So what was 10 here at n equal to 0, it becomes 10 at x equal to 2, and this is why you want to multiply everything by z minus 2. So, and this property is important. So it looks, I mean, it's immediate. It looks immediate and it's easy, but it's going to be very useful for us, especially when we do a partial fractional decomposition and trying to find the inverse. So we continue with the time shift. Of course, the story is not done yet because we haven't talked about the ROC. And the question is, what would happen to the ROC in this case? Meaning, what is the ROC of the shifted signal? So let's take a small example and then try to reason based on that example. So let's suppose that I'm not going to use the example that is here. I'm going to use maybe a different example, maybe even simpler example. So let's suppose I have the following signal, um, x of x of n equal to 10 delta n. So it's just this signal. It just has one pulse at 0 with amplitude 10, right? So x of z here is going to be equal to 10, which is a constant. So the ROC is everything. So the ROC is the whole complex plane, right? Now, if you shift it to the right, meaning if you take, let's call it x1 of n, which is if you shift to the right by one step, let's say. So delta n minus 1, then now x1 of z is going to be equal to 10 times z minus 1. So you multiply by the shift, right? Here you shifted by 1, so you multiply by z minus 1. Now, in terms of the ROC, what has changed? So the ROC is still everything except one problematic case, which is z equal to, so here you're dividing by z, so z equal to 0. So here the ROC is equal to the whole plane c minus 0, right? So we had to remove 0 from the ROC. Now, in the other case, if I shift towards minus infinity, meaning let's choose x2. In this case, let's choose x2 of n. So I'm shifting, let's take another example. I'm shifting by 3 steps to the left. So let's call it, that would be delta n plus 3, right? And now x2 of z, in this case, if you just apply the formula, or you can see it immediately here, that it's going to be, so if you want to apply the formula, so x2 of z, x of z is 10, right? And I shifted by n0, which is negative 3, so I have to multiply by z to the minus n0, which is z3. Or you can immediately see it by the definition. So usually time shift is very important or very helpful when doing the inverse Z transform rather than when doing the Z transform. And I'm going to give you an example. So now, so you see here you have 10 Z3, and now the question is, what is the ROC in this case of the shifted signal? Well, the ROC here is again the whole plane, except for one case. Actually, for Z infinity, this function does not converge. So you have to take R equal to the ROC, I mean, equal to C minus infinity, right? So, and this is exactly what the rule is saying here. So I'm going to highlight it in red. So the ROC of the shifted signal is the same of the ROC of the original signal, but you may have to add or delete the origin or infinity, depending whether you have Z minus 1 in, if you create a new Z minus 1 in the Z transform, then you have to remove the origin. Let me give you maybe one more example though. So let's suppose or you have to remove it. So let me give you maybe a little bit more, I would say maybe interesting example. So let's say x of z here in green. Let's say x of z is equal to 1 divided by z minus 1. Right, you can see that you have two poles, one at 0 and one at minus 1. But then if I shift the signal, to the, let's say to the left by n0 equal to 1, then meaning y of n is equal to xn plus 1. This means that y of z, I'm going to have to multiply by z times x of z. And here you're going to get 1 over z minus 1. So what does that mean? This means that the ROC of y is the same as the ROC of x, but z equal to 0 is not a pole anymore. So z equal to 0 is not a pole anymore. So this is what the rule says. So this is what this rule. So you have to be careful. So you may have to remove or add infinity to the ROC. So to summarize, for a time shift, when you shift to the right by n0, you have to multiply x of z by z to the minus n0, and the ROC is the same, except that you may have to add or delete 0 or infinity. Let's do an example where we apply the what we learned so far. So So here the question is find the Z transform of the following signal, which where x of n is equal 1 over 3 to the power n un minus 2. Of course, we can find this using the definition, and this example is actually taken from the slides on the linearity of the Z transform. So, but I'm going to try to find the Z transform here by using the tricks we learned so far, or the properties we learned so far. So I can write x of n here. So here you can see that there is a shift in the u, right? So, and this is kind of what I want to kind of leverage. So I can write x of n as 1 over 3 to the power n minus 2 un minus 2 here. So everything is shifted by 2. But then to match what x of n is here, so I have to write it as 1 over 3 square this signal here. So let's call this signal here y of n, right? So or this is y of n minus 2, I mean. So y of n is equal to 1 over 3 of n u of n. Okay. And now I know from what we've learned before that y of z is equal to z divided by z minus 1/3 from what we learned before. And now because this is a right-sided signal, so z is greater than 1/3 here. And now I can apply the formula here. By linearity, I know that x of z is 1/3 times the z transform of y of n minus 1 is z to the power minus 2 y of z. Again, the minus 2 here is coming from here, so this is why, because I have a shift. And actually here, instead of being 1 over 3, this should be 1 over 3 square. Because it's 1 over 3 square there. And now what I can do, I can just replace y of z by its value. So I have 1 over 3 square, z to the power minus 2, and y of z is z divided by z minus 1 over 3. And now you get here 1 over 9. You're going to have here z to the power minus 1 divided by z minus 1/3. And if you multiply both numerator and denominator by z, you get 1 over 9, 1 divided by z minus 1/3. So you can see here that you created a new pole, which is z equal to 0, so which was not there before you shifted the signal. But we know that the signal is left-sided, or here it is right-sided. So if we find the ROC, it's a rational function, right? So the poles are 0 and 1/3, and since it is a right-sided signal, so the ROC is going to be outside the circle going through the pole with the largest magnitude. So although we created a new pole at z equal to 0, it doesn't affect the ROC. So here the ROC stays the same. Here I want to show you how we did this example last time. So last time what we did is we just applied the formula or the definition, and this is what I'm reproducing here is the same slide you saw in the example, I think, on the linearity of the Z transform. So anyway, so basically here I show you how you could get the Z transform of this signal by just applying the formula, and you can see here that you get exactly the same result. So you can see that if these formulas can be handy if you can remember them instead of just going through the mechanics of finding the Z transform by applying the definition. Property 3 is about scaling the signal, and here by scaling I mean given a complex number a, and the signal xn is multiplied by the scalar a to the n. So I'm scaling, multiplying the signal by an exponential signal a to the n, and then the z transform in this case is the same transform as x, so it's x of, but the of z by a. So I'm dividing z by a. So to see where this formula come from, let me maybe prove it. So if you call this guy here, or I'm sorry, if you call this guy here y of n, then you can see that y of z is the sum of y of n z to the power minus n, and then you replace y of n by its value, so it's a of n xn z minus n, so it's gonna be sum of x of n z by a to the power n, and this is y, so this is exactly x of z by a. So you just replace, instead of z, you scale z by dividing it by a, and the ROC is the ROC in the scaled plane. So everything is multiplied by the norm of a. For instance, to see why this is true, just let me give you a small example here. So let's suppose in this case, the ROC of x of z. X of z is, let's say it's a right-sided signal and it's the exterior, it has a pole at 1, so it's the exterior of this circle. Then the ROC of x of z by a is gonna be, because I scaled everything by a, so here is z greater than 1, right? And for this guy here, so you think of z here, it's the argument, the norm of the argument greater than 1. And here is same thing, the norm of the argument greater than 1. So it's going to be z divided by a greater than 1, which means that z is greater than, the norm of z is greater than the norm of a. And this is how you get the ROC of the scaled signal. So here, so everything is scaled by a. So here it's the outside of a signal of a circle going through 1. Here it's the outside of a signal going through a. So that's what this means. Usually it's just easier to just whenever you have this. I mean, if you can notice it in the signal that it's multiplied by a to the n, then you can apply it, of course. But usually, at least for me, I find easier whenever I have these things just to do the formula. An interesting thing is when I choose a to be, so here it's supposed to be a, the constant, is ej omega 0, so this is so it's this complex number, which is on the unit circle, and the angle is omega 0. Then when you multiply the signal by ej omega 0 n, so this may be a formula that may appear, that may be useful more than the general formula. Then the z transform is x of e minus j omega 0 n by z. So because this is z by ej omega 0 n. So what you're doing is actually rotating the scale, the z plane. Why? Because if let's suppose that z written in the polar coordinates r e j theta, then when you multiply by e minus j omega 0 n times z is going to be equal to so what's that gonna be? So this is going to be, sorry, here there's no n. There is no n here. So because this is basically ej omega 0 to the power n. So this is basically when you multiply e minus j omega 0 times z, it's going to give you e minus j, or e, if you want, j theta minus omega 0, and you have the amplitude here. So what you're doing is you're rotating the angle of z. And for this specific case of scaling, the ROC is the same. So here let me write it down. So the ROC does not change because you have to multiply, because the amplitude of ej omega 0 is equal to 1. So you have to multiply everything, the ROC by 1, and it's still the same.